Okay, in a minute we're going to solve for a particular solution to the same left-hand side, but with a different function on the right-hand side. But let's make sure we understand what we've done so far and understand the general lesson we can get out of this. We had a particular, we were seeking a particular solution where the right-hand side, the non-homogeneous part, was t squared, and we ended up trying a second-order polynomial. We can kind of generalize this idea. If the right-hand side of the equation is a polynomial, our trial solution should generally be a polynomial of the same degree. So we had a second-degree polynomial here. There was just one term, but this is still a polynomial with a t coefficient of 0 and a constant term of 0. Okay, so here's a second-degree polynomial, and we try a general second-degree polynomial. We get three equations for the coefficients of that polynomial, and we get a particular solution. Now that's not going to work when our right-hand side is cosine of t. So let's ask, what would you have to take derivatives of to get the cosine of t? Now, that last clip went on for a while, and I had some stuff written down here, but I want to rewrite it so you can see it develop. In order to get a cosine of t by taking derivatives of y and combining them with y, we generally are going to need some function that includes multiples of the sine and the cosine of t. Now it's going to turn out here that we don't really need the sine of t, but in general, if we had a y prime term in here, we would need the sine, and you'll see why that works when you do a few of the problems, or why that's necessary. Okay, so we're going to use derivatives of sine. We're going to get a cosine of t, we need derivatives and higher derivatives of sines and cosines. So we're going to try a particular solution of the form a cosine t plus b sine t. And we can easily verify that the second derivative is going to be negative a cosine t minus b sine t. And that's going to give us the equation yp double prime minus yp equals negative a cosine t minus b sine t minus the quantity a cosine t plus b sine t. And when we collect terms, we simply get negative 2a cosine t minus 2b sine t. And that should equal our right-hand side, which is the cosine of t. So that the coefficients of the cosine have to be the same. The coefficients of the sine have to be the same. Now, our right-hand side was cosine t. It had no sine t, so we're going to actually go ahead and write this in, that we have a 0 sine t. It's not necessary to write that, but so that we can see that the coefficients of the cosine are coming out equal, the coefficients of the sine are doing the same, we go ahead and include this. So we get negative 2a has to equal 1. That's the coefficients of the cosine t have to be equal. And we have negative 2b equals 0. The coefficients of sine t have to be equal. Our solution is simple. A has to equal negative 1/2. B has to equal to 0. So that our yp of t function, which is a cosine t plus b sine t, is, well, write it out, a cosine t plus b sine t is negative 1/2 cosine t plus 0 sine t, which is just negative 1/2 cosine of t. Then our general solution y of t equals yc of t plus yp of t. is going to equal our characteristic solution, which is C1 e to the t plus C2 e to the negative t, then minus 1/2 cosine of t. Our characteristic solution here, our particular solution here. You can substitute this back into the equation, and you'll find that no matter what the values of C1 and C2, that these terms will subtract off. They'll go away, leaving us with just the second derivative of negative 1/2 cosine t minus the negative 1/2 cosine t, which will come out to cosine t.